Thank you. Hope it works. It works. Sure. Does anyone hear me? So nothing happened this time? No. Okay, I'm not hearing anyone.
We could see it.
Oh, okay.
We
so
can
now
see it. We can see it. Your share. We can see the sharing.
Okay. I'm glad to show you my work. My field of study is deep learning, but this time I'm gonna present you a part of it. I'm regarding reinforcement learning. So as you can see from the title, it's basically I'm using a game engine to train intelligent agents using reinforcement learning. So I started by implementing from scratch in C# a deep learning library that I applied afterwards. I implemented deep reinforcement learning algorithms and used them afterwards to train simulated agents in Unity, which is a game engine. What I plan for now is to show you how the process works and how do they train in a short manner and see my results. So I'm starting by, at first we are creating the agent, okay? So I'm using a 3D software for 3D modeling software like Blender to build up our agent. I choose for this presentation to be a walker, which his task is to run forward for as long as possible without falling over. The model, the 3D model, is exported in a 3D model format and then imported into a game engine. I'm using Unity for that. Of course, in Unity, there is an after processing, like I'm adding collision boxes for each body part, or rigid bodies to simulate physics, let's say friction or gravity, and nonetheless joints to connect the body parts, the 6 degrees of freedom joints to simulate the actual movements of the agent. Moving further, so we have our agent working now, okay? And the training part works by letting him interact with the environment. Of course, we are not using just one, but we're using more in parallel to have a more efficient training. So let's say he collected some steps, a discrete sequence of time steps. For this example, there are just 8. We call this a trajectory. And we are storing for each single time step the state of the agent. The state means what he sees, or let's say any information that might be important for him, like the rotation of the joints, the velocities, the angular velocities, and so on, and the action that the agent took given that state. So for each state, he takes an action and see what's going on. As I said before, our task is to make the agent to learn moving forward. So for that, he awaits a signal to know what's good and what's bad in what he's doing. So for this example, let's say we are modeling a reward function that promotes or gives him a reward signal for every meter he reached. Let's say he reached that 1 meter at the step 7. What does it mean? It means that the action 7 that he took, given the state 7, it's a good one because he received the reward. But not only the action 7, but all the previous actions that lead indirectly to receive that reward. Of course, but we are not rewarding them with the same value, but in a discounted manner. Of course, this applies to penalties as well. Let's imagine our agent touching the ground with a hand when we don't want that. So we are penalizing him. And of course, the reward and the penalties are summing up. Basically, sometimes they're canceling each other. And there are also some algorithms that takes in account the randomness in the actions that he took. Why? Because we know the paradigm in reinforcement learning, the exploitation problem. Yeah, we want our agent to explore the environment to find higher and higher rewards. Moving further, let's see what does the brain consist of, the brain of the agent. We know that we are using deep learning. So for that, it's basically a neural network that, for those that never entered in deep learning or so, you can see it just as a black box or a mathematical function that receive an input S. S is not a scalar, it's a vector of values and outputs a vector of actions. And of course, the policy needs also a critic. Most of the state-of-the-art algorithms are an actor-critic methods. And the critic basically receives as an input the tuple of the state and the action from the experience buffer that he collected before. And he is trying to predict as accurately as possible that reward for those state action pairs. In this scenario, I said the reward, the penalties, and the stochasticity in some algorithms. Okay, so the critic helps the policy to update, to find the direction of the gradient, to optimize itself, to choose better and better actions. Of course, there are algorithms that are not using just a simple policy like that, but instead they're using two networks, one that yields a vector of mean values, and the other a vector of positive standard deviation values. And these ones are parameterizing multiple one-dimensional distribution, Gaussian distributions. And from that, we are sampling the action. And this is basically a method to inflict stochasticity, randomness in the actions. Moving further, I'm planning to show you some algorithms or how the objectives look like, mathematically speaking. So all the algorithms in reinforcement learning are trying to maximize the log likelihood of an action. So we are trying to maximize the probability for that action to appear. And this is defined by this pi, which is the probability distribution of the policy that is parameterized by the policy, the network we know. And what is this A hat? A hat represents the advantage. And I'll show you an example for now. Let's suppose that our agent collected a lot of training data. And of course, not only the agent trained, but also the critic. We know that the critic trains to predict as accurately as possible the reward for a state action pair. Okay? And let's say we run again the agent to collect some steps. And we observe suddenly that the action that he took, let's say it has a reward higher than the critic expected. So from all the average estimate in the past, these actions that he newly had is better than the average. And it means that it has a positive advantage. Okay. Also, there are more algorithms. So the first one was vanilla policy gradient, the basic one, and we can see this optimization problem as a hiking, sort of hiking. We assume that we are trying to reach the peak of the mountain here, which means that that point is the highest reward possible we can get from an environment. And we are trying to take steps towards the peak. The advantage is telling us what is the direction and the magnitude of that step. And here you can see another algorithm. It's called proximal policy optimization, which is basically doing the same thing, but in another manner. It inherits from another algorithm called trust region policy optimization that works like this. I I mean, we see that in VPG, a step, let's say here in the middle of the mountain, for a, let's say a batch of training data, the direction of the arrow might point a little bit sideways. And if the direction of the, let's say the gradient, it's basically falling off the mountain completely, and it's a catastrophic event. It can be very sensitive, and it can unlearn everything that he learned. And proximal policy optimization optimizes that by creating a trust region. So basically the agent just takes small but safe steps towards the peak of the mountain, towards the objective. And this works by, I mean, in TRPO, it works a bit different. It computes the callback library divergence between the old and the new update of the distribution. And if the distribution changes too drastically, the training stops. So it does not allow large updates in the policy. And PPO works the same, just includes this directly into the objective function by clipping the ratio between the old and the new and the old policies. And another algorithm that I like the most, it's soft actor critic. It's a bit more complicated than the previous ones. Firstly, I will start with the first part of the equation. Soft actor critic uses two critics instead of one, because a single critic is starting to overestimate the reward for that state action pair, and we are using two critics for that and take the minimum between the two. And the second part makes this algorithm special. Why? Because it promotes high random actions. So it subtracts the logarithmic, the log likelihood of the actions. I said before that sometimes some algorithms remember the stochasticity of the actions. This algorithm does that. And basically it's just forcing the policy to take random actions to find newer zones in the environment. And it's one of the best algorithms because it, even if it's costly, computationally speaking, it converges to better solutions than the previous ones. And I'm quite done with the presentation. Just the results. I trained quite a lot of agents, really. The worker, another one that has to sort some tiles, and he must visit each other in a ascending order. Crawlers, also multi-agent environments, and so on. Also, everything is open source, so which is the ones who are very interested in this field and know how to implement or what is going behind popular deep learning frameworks like PyTorch can check this out. It's in C# or Unity game engine. And as a sample, I couldn't include it here in the presentation, but let's see. So this is our agent, 0 hours of training, nothing special. He's falling over all the time, but after 12 hours, it's moving forward. It does his job quite perfectly, never falling apart. And that's all. Any questions, please?
Thank you.
At the moment, your presentation is so technically, I can't understand what is your use case for this research.
Yeah, it's not really I'm not trying to compete PyTorch, for example. My idea was to implement those things just for educational purpose, but it has potential really, because it's easier to use comparing to, let's say, combining PyTorch with Mujoko, which is another framework for deep reinforcement learning. And it's, yeah, nothing special to say more. Quite,
Okay.
that's all.
Okay, thank you.
Thank you as well.
Thank you again. Next presentation will be Mihaly Koniczka.